Hi, my name is Stefanos,
Hi, I'm Lane.
Hi, I'm Karsten.
and today we're doing activity number 1 for our first project for this class. So, for this activity, we know the mass of the box is big M, and the radius of the table is big R, and the mass of the ball, or the halo sphere, is small m, and the radius of the halo sphere is small r. We know that the angular speed of the table is constant and the pulley is ideal, meaning that the string is massless and the pulley is massless too.
All right. So some of the assumptions that we're going to be making for this activity is that the string around the ball will unwind, and it's not stated there, but that it is also infinitely long, so it's not just going to randomly stop. We're going to assume that gravity and tension are like the two only important interacting forces. We obviously know that there's going to be more than that, but they're going to be the two that are going to be driving like the interaction that we will see. And the box will move with the turntable because this was kind of weirdly worded. It said it was frictionless, but that wouldn't really necessarily make sense. So we were just going to assume that the box will move with the turntable despite it being frictionless. And what we are ultimately trying to find is the angular speed of the table so the box of mass M does not move.
So here we have our free body diagrams for this problem. So the first one we have is the free body diagram for the mass. We got our force of gravity on the mass by the Earth. We have a normal force on the mass by the table, and then we got tension from the rope on the mass. And our second free body diagram, we have the sphere with mass little m. We have force of tension from the rope, and then we got a force of gravity from the Earth. And then we also have some diagrams. We have side view of the turntable, where we have our big mass M and our small mass M, and we have a radius of big R. And then we also have a like 3D version of the turntable with the same values.
Okay, so the relevant physics formulas for this activity is 1, centripetal acceleration, since we know it's going to be a uniform motion. 2 is torque net. The second one would be F net ma. F net equals to ma. And then the angular acceleration and the angular velocity, and also the torque net, which is used to calculate the torque that's going to happen from the halo ball spinning out. And then also we have inertia from center of mass for the halo ball.
All right, so when we went about calculating the symbolic answer to this, we first started with F net equals ma, and we determined that the net force acting on the system is equal to the mass of the sphere times gravity minus the force of tension that is created by that. And then we knew that we could calculate some torque force that was created from the ball, which is torque net is equal to R force of tension sine of 90, which is equal to I alpha, which we could then kind of derive into R force of tension is equal to I times A over R, which we could then further refine to get the force of tension is equal to IA divided by R squared. And then we use that and we plugged that in with the inertia of the hollow ball about its center of mass, which we put in here to derive an equation that would ultimately get us that the acceleration is equal to 3/5 gravity. When we plug that back into the force of tension equation, we're able to determine that the force of tension is equal to 2/5 mg. Since the only force acting on M is the force of tension that's pulling it along the surface, we know that M times A is equal to the net force, which is centripetal acceleration, which we could then write as capital M V squared over big R is equal to 2/5 mg, and we used the other equality up here to get m omega squared r squared over r is equal to 2/5 mg, which we then further refined down to get that our angular velocity is equal to the square root of 2 mg times 5 capital M capital R.
Okay, so now that we have our equation for omega, we can plug in some values. So for our so we're going to assume that our big M, the mass of the block, is 20 kilograms. Little m, the mass of the sphere, is 10 kilograms. We're going to assume our big R is 1 meter, and then our little r is 1/4 meter. And we can just plug all that into our equation for omega, which will give us 200 kilogram meters per second squared over 100 kilogram meters, which you can simplify to 2 square root of 2, which comes out to about 1.41 radians per second. Alright, so we're going to do a units check for this problem. So we know omega is radians per second, and for our answer we got kilograms times meters per second squared over kilograms per meters square rooted. And so if we simplify this down, we get a square root of 1 over seconds squared, which is equal to 1 over seconds. And we know that radians is unitless, so we get radians per second, which checks out with what we know that omega should be.
Alright, so the physical answer that we got makes sense because 1.41 radians per second gives around 1 rotation every 4.5 seconds, which is around 13 RPM. That is a little bit slow, but relatively speaking, the turntable is quite large. 1 meter radius gives a 2 meter diameter turntable. That's quite big. And that means that the mass of the box is further away from the center and experiences stronger inertial forces from the turntable spinning as a result. So it doesn't necessarily need to go as fast in order to kind of cancel out the forces of the hanging sphere. And although this is not exactly the same as activity 2 on homework 4, it is similar, as both of them we are trying to find the angular velocity of a spinning disk. The other one involved a collision, this one more or less involved just unchanging system, but they are similar as we were trying to find the angular velocity for both. And this activity is also similar to several of the studio problems involving spools and the respective interactions with pulley systems that the spools have, as with the falling sphere.
So our symbolic answer makes sense because as the mass of the sphere approaches 0, so does the angular velocity, and that makes sense because the net external force that is being applied on the whole system is only coming from the sphere. So as that approaches 0, there's no need for angular velocity. So it would make sense why the angular velocity approaches 0 as well. Our answer also makes sense because as the mass of the block increases, we also have to keep in mind that the tension force coming from the sphere is staying the same. Therefore, it won't be as effective at pulling the box inwards. Therefore, the angular velocity needed to keep the box on the edge will decrease. Okay, so I wanted to add to the work me and my group did, kind of more of adding more explanation and clarifying a couple things. So for the portion where we used the torque of the ball's rotation to find the angular acceleration, and finding a way to connect that to the F net equals to ma of the translational motion of the ball. That we were able to do that only because the ball was rotating in uniform circular motion, and we went over that on studio number 3 for torque analysis, and specifically on activity 3.3, which was the hoop slipping. And we weren't able to apply this formula right here of alpha equals to A over R because it was not uniform circular motion and the hoop was slipping. But for this specific problem, we were able to make that connection where we used the force of tension times the radius equaling the moment of the moment of inertia times this right here would be alpha, which is the same as A over R. And we were able to make this switch right here because we know it's a uniform circular motion. And additionally, we were able to relate that to A right here or to the acceleration of the translational motion of the ball falling because it's a uniform circular motion. Now looking at clarifying some of the sense making and the special case analysis, I want to show how the angular velocity decreases when the mass of the box increases. So I'm gonna stand right here. So right here the F net of the box is just gonna be the force of tension times its mass and the centripetal acceleration because it's going in uniform circular motion. The turntable is moving in a uniform circular motion. We know that centripetal acceleration is equals to v squared over r. In this case, this radius right here we know that this radius right here is r, or big R. And we also know that since it's a uniform circular motion, v would equal omega times big R. And simplifying that down, we get this. Force of tension equals to big M times omega squared times big R. Now, if we use the special case analysis where we increased big M, or the mass of the box, the angular velocity would have to decrease. Now, how does that make sense? The only way that makes sense is we know that force of tension is staying the same. We know that the radius is staying the same, meaning that the box isn't going to get any closer to the center, or it's not going to fall off the table. Those are some important assumptions we need to make. If these two are staying the same, when the mass increases, the angular velocity right here needs to decrease. So that was an important sense making for this project that also helped me understand the physics behind it.